Guys, I apologize if I look like garbage. It's because I feel like garbage because it's finals week and I've contracted some mystery illness that has made me cough so hard that I pulled a muscle in my side. Today we're going to be talking about the worm again, but this is for a different class. I'll link the video at the end. You can check it out. I just made a video about our clinic project. But this video is going to be about failure analysis of one of the components of the worm. So this is the worm. I'll keep this part short. It's a little flappy boy and compresses and decompresses to move forward in an inching motion. The problem we were having with this robot is that the servos kept failing. The servo is that little black guy there that's been circled. So the servo, after a certain number of cycles, would just stop. We measured the current draw, and the current draw was about 0.36 milliamps. And you can see from the data sheet that that was clearly not enough to fry it. But one thing we did notice while we were running it is that it got extremely hot. So we were thinking maybe it's exceeding this 55-degree temperature range. So to test this out, we hooked up the servo and we passed it maximum value that it could take. And then we put a clamp on it. And you can see that when we increase the pressure on the clamp, it would increase the current draw from the servo. The current draw is still well below the threshold that's listed in the data sheet. So we took some steps to see how hot our servo was getting.
To find out whether or not the servo was overheating, we decided to model the servo with some hand calculations. Here we can see that we have heat coming in as a result of electrical power delivered to the system, and that the same heat was being lost to radiation and convection. We stated our givens. The room's temperature was found to be 22.3 degrees Celsius, so this is T surroundings. The voltage across the component was measured at 4.33 volts. The current varied between 0.31 and 0.41 amps, but we will assume, for the sake of calculation, that it was 0.36 amps. There was no air movement over the servo, so we assume natural convection of 10 watts per meter squared Kelvin. The surface area of the servo exposed to air was found to be 0.0024612 meters squared, and the emissivity of the servo plastic was found to be 0.87. We want to find the steady state temperature, so we assume that the heat entering is equivalent to the heat exiting. We can also assume that the amount of heat entering the system is equivalent to the power delivered to the system. So what we're going to do is say that the Q in is equal to the power, which is voltage times current. We now combine these equations to say power delivered is equal to the heat being lost via radiation and convection, since those are the two mechanisms we are considering here. We then replace Q dot radiation and Q dot convection with the expressions that are used to calculate those values. We then plug in our givens, and finally we solve for a value of x is equal to 61.8 degrees Celsius. Now, this is already above the 55 degrees Celsius value listed on the datasheet, but we still have some more work to do. We used Excel to model the equation transiently. The table on the right shows the givens used. We changed the equation from the last section to include mc dt over dt. The table on the right is the data from the Excel modeling. We plug these into a graph and see the temperature level off at 119 degrees C after about 20 minutes. The next step is to compare these values against the SOLIDWORKS results.
The next step was to model the servo in SOLIDWORKS. We modeled the servo in three pieces: a dial, a front, a motor, which acted as the heating element since the power was being delivered to it, and the back. We ran the results with natural convection, and we found that the servo got up to a temperature of 389 degrees Kelvin at steady state, which is 115 degrees Celsius. So the results between the SOLIDWORKS and the Excel simulations were pretty close. Here we have a little animation showing flow over the servo. The next step was to compare our simulation and hand calculation results to the real thing. To do this, we used a thermal camera that we borrowed from Dr. B. final temperature we captured on the thermal camera was 100.8 degrees C, which is only 15 degrees C off from the SOLIDWORKS results. 15 divided by 100 is an error of 15%. In the end, we were able to determine that the temperature was exceeding the 55-degree limit that was listed in the datasheet, and that is why the servo was failing. In the future, we would want to design the system such that the load on the servo was minimized and it wouldn't overheat.